Okay, the second question says identify the difference between volts, current flow, and resistance in a circuit. So in the future, you're going to see questions, various types of questions. They may be something as simple as, what is voltage? Where it has you just write the actual textbook definition. But more likely, what you're going to see are some technical questions, and you're going to see these as you take these quizzes, where it says something like, Technician A says that current flow in a circuit remains the same. Technician B says that resistance will change. Who is correct? So in order to answer that question, you have to be able to understand what it is that these two technicians, or these two people, are discussing. You need to be able to decide, is this correct information or is this incorrect information? So if you take this down in your notes, you should be able to look back and reference that, read the question and say, oh, this is not correct or this is correct. Okay, so starting out, volts, if you look at your sheet here, all three of these are referenced on the very front page of this, and they're abbreviated with letters. So volts is going to be abbreviated or outlined with either the letter E or the letter V. Now, why would we put the letter E for volts? Doesn't seem like it makes much sense, because the word volts does not contain the letter E. Here's why. The E stands for electromotive force. That's another term that can be used to relate to voltage. So, depending on what you're looking at, you might be reading one of these textbooks over here. The textbook was written by somebody else. Then you might be reading some information on today's class or reading from a different textbook. Every author or every person that you talk to, they might reference the same material different ways. So voltage is the same thing as electromotive force. And when we're talking about it in terms of a circuit, voltage can be thought of as the pressure in a circuit, or the push that's behind something else in a circuit. So anytime that I talk about these three things, I like to use a garden hose as a reference. How many people have ever turned on a garden hose? Okay, pretty simple task. You might use it to fill up a bucket or wash your car or whatever. So, on a garden hose, and I'm talking about the actual hose, what is usually on the end of the hose? Something that you squeeze. What would we call that? Speak loud. A nozzle. Yes, that's correct. So most of the time, you're going to have a nozzle that's on the end of this hose, and that nozzle is going to be a restriction. That's going to represent resistance. So let's think about this. What we do when we're going to use this hose and this nozzle configuration, the first thing we have to do is we have to turn on the water. We have to turn on the valve. Now, when we turn on that valve, if we have this nozzle on the end of our hose, if everything is sealed up, does any water come out of the hose? No. You control that by squeezing it. Okay? So when you turn on that nozzle, the hose will swell up because it's filling up full of that water, but it's under pressure. So when you're thinking about volts, think about turning on that nozzle or turning on the valve. A car battery is the same way. A car battery contains 12 volts. This 9-volt battery contains 9 volts. So this contains electrical pressure right now. But we don't have to use it all the time. We want to use it when we want to use it. So we only want water to come out when we squeeze the nozzle, or we only want electricity to be flowing when we turn the switch on to activate a light or whatever. Okay, so volts can be thought of as electrical pressure in a circuit. Now, current flow. We established when we talked about the basics of electricity, we talked about current. Current is the movement of electrons across a conductor, or the flow of electrons across a conductor. something important to take note of. Up here, voltage is measured in volts. So I didn't write that down because you can probably figure that out for yourself. Volts is an abbreviation of the word voltage. So when we're measuring voltage, we're measuring it in volts. Current is a little different. Current flow is going to be measured in amps. Okay, so this is another one of those things that may be interchangeable in the future. When we're talking about current flow, the question may be talking about amps. So it may say technician A is measuring amperage in a circuit. What that means is that the technician is measuring the current flow. Amps is just a unit of measure. When we look at a fuse, we talked about these the other day. These fuses are rated in amps. So this number 15, this means that this fuse has a capacity of 15 amps. If we exceed that, the fuse's job is to blow or open the circuit. So we've got these in 5, 10, 15, 20, 25, 30, 40, 50, 100, and they also are color-coded. Okay, so current flow is the movement of electrons. So going back to the garden hose analogy, the actual movement of that water through the hose is the current in the water hose circuit. Now, resistance is anything that opposes that current flow. In an electrical circuit, resistance is going to be measured in ohms. And ohms can be abbreviated with a symbol. It's kind of like a horseshoe. It's the Greek symbol for omega. Looks something like this. And that information is also in this packet that I gave you. Okay, so going back to that garden hose analogy, we can change the resistance of that nozzle. If we pull the nozzle handle real tight, we get a real tight stream or a flood of water coming out at a pretty decent pressure. If we just barely crack that nozzle, then we get that fine mist of water. Very, very low current flow. So we have a high resistance. In that nozzle, we can control the resistance. So we can do the same thing in a car, but before we get there, let's talk about the relationship between the two. It is exactly the same in the garden hose as it is in a real-life circuit. Okay, so current flow. If we have very low resistance, which means that our garden hose, our trigger is squeezed all the way. If we have very low resistance, there's not a lot of opposition to the movement of that water, then we have quite a bit of water at a high rate of pressure coming out of the end of that nozzle. So that's what you would do if you're trying to spray something off. So, in this analogy that we're talking about, when you turn on the nozzle, or when you turn on the spigot, the water spigot, the pressure in that spigot stays the same. Your water pressure at your house is going to be whatever it is. A car battery is going to remain at 12 volts, or very, very close to it. So, this does not change 99% of the time. This pressure is going to remain the same. The current, the flow, or the movement of that liquid, that water, it is going to be determined by you, by how much you squeeze the nozzle, how much you change the resistance. So, if we squeeze it again, if we squeeze it real tight, we have a lot of water, a large volume of water coming out. If we just barely squeeze it, then we have a high resistance. We have a major restriction on the end of that hose, which means that we have a mist of water, very little amount of current flow. So use that information to answer this question. So in an electrical circuit, voltage remains the same. This does not change. The question says, if resistance increases, so if we barely crack that nozzle, what is going to happen to current flow? This is a relationship that stays the same all the time. All right? So the answer is, current flow must go down. It will decrease. And this is a rule. So you could write this in the notes on this packet that I gave you. This is true all the time. If voltage remains the same, and it does most of the time, okay, if voltage remains the same, and it does, now keep in mind, when we're talking about car batteries, and we haven't got there yet, but we will very soon, car batteries are actually 12.6 volts. But you'll hear me reference 12 volts. That's just to keep the math simple. It eliminates the need for the decimal place. 12 is a pretty round number, so it's easy to do the math associated with this type of work if we just take the decimal out of the equation. But you have to remember that a 12-volt battery is actually slightly more than 12 volts. So this can change slightly, but less than a volt at a time. So we're talking about a half of a volt change. That's not a major enough change to have a direct impact. So voltage remains the same. Current flow and resistance are directly affected by each other. So that means that if one changes, the other one has to do the opposite. In this scenario, if current flow increases, that means that resistance has to decrease. As resistance goes up, current flow must go down. So if resistance is high, current flow is low. If current flow increases, resistance must decrease. They're directly proportionate to one another. Okay, so one is low, the other will be high, and they change a lot. So I can give you tons of examples of that. When you're talking about light bulbs, for instance, there are certain light circuits on your car that will get brighter and dimmer. One of the most common ones is the dash illumination. Almost all cars have a control where there's a little thumb wheel on the dash somewhere, or a knob that you can turn left or right, and if you turn it to the left, it will get dimmer. The lights on the dash will start to dim out. If you turn it back to the right, or thumb it up and down, then they get brighter. What we're doing here is we're using this knob to change our resistance in that circuit. If we want the bulbs to be dimmer, we are going to increase the resistance. If we increase the resistance, it is going to decrease the current flow, which means that the bulbs aren't going to be as bright. Some people have sensitive eyes at night, and they don't want it to be super bright. Then there's other people who want it to be real bright so they can see very well. So if we want the light bulbs to be brighter, then we're going to decrease the resistance by turning that knob, and that's going to increase the current, making the bulbs illuminate more. So there's all kinds of examples of that on a car. Another one is your blower motor. On your car, you've got heat and air conditioning, and then you've got your little control station. So if you turn it all the way off, that means there's zero current flow. There's no current flowing through that motor because it's not turning. If we want it on the lowest setting, we turn to the 1. So in that circuit, there is a blower motor resistor. The current goes through a very high resistance, and that limits the current that gets to the motor. So the motor turns very slow. You get just a little bit of airflow out of those vents. But if it's really, really cold or really, really hot, typically you want to get warm or get cool very, very quickly. So you turn that thing all the way up to 4 or 5. That has a very low resistance, which means that that blower motor is getting all of its current that it can, and it's spinning very, very fast and blowing a lot of air out of the vents. So you can change that to however you want to be comfortable by turning that knob. So all of this is very, very important information. You're going to hear me reference these 3 words over and over and over and over again. You're also going to be doing some math in the near future, figuring out how much current flow a circuit will have, how much resistance a circuit will have, and how many volts will be present in that circuit. There's a mathematical relationship between these 3 things, and it's called Ohm's law. That's on the very front page of that packet that I gave you. So once we establish all this information, then we'll get into that. We're going to spend a few more days just making sure that everybody's familiar with this. Okay? So these 2 questions. If I were you, I would write these down. I would write every bit of this down because you're going to use it in the future. In an electrical circuit, if voltage remains constant, resistance increase, what will happen to current flow? Decrease. So I'll leave that on the board for another few minutes. You can write it wherever you want. Not telling you that you absolutely must write it down, but it will help you in the future.